Yes. All right, cool. Sorry for the delayed start. The whole crowd strike thing and everything like that, having to get that installed on like the Surface tablet that I use. Took a moment, right, because it's university owned. And I forgot to do that when everything was happening because it didn't need to at that point. Anyways, let me get straight into this. Acids and bases, titrations, and redox stuff is what was on this packet. And so B5, the number one thing that was voted on. So in this case right here, right, what the question is asking for is a titration was performed on a 25 milliliter sample of aqueous ammonia solution of unknown concentration. And then I'm giving the KB value, right, the base dissociation equilibrium constant of 1.76 times 10 to the negative 5. And so it required 36.78 milliliters of a 0.0105 molar HCl aqueous solution to reach the equivalence point. Determine the following. So the first question that we have right here, right, is what type of titration is being done, right? So this is a weak base, because that's what ammonia is, right? So it's a weak base, strong acid titration. So if we just simply plot out, right, what we have here is pH on the y-axis, and on the x-axis, right, we have volume, HCl added, right? What should happen is that you're going to have, a high pH initially, right, because we're working with a base, and so it's going to be up here somewhere, and then it's going to level off for a while, and then eventually it's just going to have a huge dip down, and then it's just going to become acidic from that point forward. So if we go through everything, right, so this right here is our initial pH then, right? This region right here is what I would refer to as the buffer region, right? Because in this region, what we're looking at is both having a significant amount of both the ammonia, but also the ammonium, right? The conjugate acid that's going to be present in that case. And so that's right there is actually going to be, essentially like a buffer. Halfway in between this point right here, right, is where we're going to have the pKa is going to be equal to the pH between those 2 points. And right, and you can prove that to yourself, because halfway between those two, right, the concentration of the ammonia should be equal to the concentration of the ammonium ions in those cases, right? And so if you take the log of 1, right, which is what it would be in that case, right, that's equal to 0. And so then pKa plus 0 is going to be equal to the pH. And so that means pKa is equal to the pH, right? So that's one thing to always think about within a titration, is that there's going to be a point where the pKa of the weak acid or weak base or whatever, right, that you're looking at is going to be equal to the pH, and right, and that's going to be then the halfway point between reaching the equivalence point and your initial pH in those cases, right? And then your equivalence point, right, is going to be then right here, right? It's going to be halfway in this point right here. So equivalence, right? So we have this, huge drop off in this case, right? And then we have right here, right? So this is all going to be HCl dependent, right? This is going to be all just simply H3O plus, because at that point, all of the ammonia should have been converted into ammonium, and the ammonium, right, is going to be a weak acid, and so it's going to still have that weak acid, weak base equilibrium, but if you're adding more and more acid to it, right, it's just going to keep on shifting away from forming, the any kind of base, right? So it's going to be completely dependent upon, the amount of acid that you're adding at that point, right? That's going to be changing the pH in those cases. So that's right there. So that's the sketch of what, a simple weak base, strong acid titration looks like, right? With a lot of labeling of what we should expect in each region. And a really, even if it's not asked for, I think on the exams, it's always helpful, I think, to identify the type of titration that you're doing, if there is a titration question, and sketching this out, because then this will let you know what equations to use and what to do in those cases, right? Because if we're in the buffer region right here, right, we can use the Henderson-Hasselbalch equation, right? That should be, pretty standard in that scenario, right? So we have the Henderson-Hasselbalch equation, so that makes that very easy to calculate what the pH is, right, at the equivalence point right now. NH4 plus dominant. And so now you have to make sure that you're paying attention to the type of acid-base equilibrium that you're doing, right? So in that case, you need to flip around what you're doing, right? So beforehand, right, you're going to be writing it out as if you're doing the base dissociation, right? If you're going to go that route, right? If you aren't going to use the Henderson-Hasselbalch equation in that case. But from at the equivalence point, because you've consumed all of the ammonia in this case, right? All of the weak base and converted it all into the conjugate acid, because now it's all the conjugate acid, that's still going to have an equilibrium in that scenario, but you have to then make sure that you're then flipping it around, because now, right now, you're going to have all of those moles that you had before are going to get converted now into, the conjugate base of that, acid in those cases, right? So, and same thing, right? If you're doing a weak acid, strong base titration. And then once you're past that equivalence point, right, any HCl that you're adding at that point just simply becomes the dominant species. You can completely throw away and ignore any kind of, weak acid, weak base equilibria for the most part, because it's just going to simply be completely driven by the H3O plus in those cases. So, but yeah, so that's an important thing, right? And that's, I think, a good approach to take to any of these titration problems is drawing out what it is that you're looking at. Even if the question doesn't ask you to do it, right? Draw it out so that you know for yourself, label everything, so that way you can get an idea of what equations to use, right? What the situations are in those cases. So, cool. So now, right, part B is what is the concentration of ammonia in the original solution, right? And so if we know that it took 36.78 milliliters of a 0.0105 molar HCl solution, right, to reach the equivalence point, right? The equivalence point is when the number of moles of the titrant is going to be equal to the number of moles, right, of the starting material that you have in the thing, right? Those are going to be equal to each other. The concentrations, right, are going to be different because the volume is going to be constantly changing between the two of them. But the, that's the definition of the equivalence point, right? Is that they're going to be 1-to-1 in those scenarios. So to calculate what the concentration of the original solution is, first we need to calculate how many moles of HCl we had actually added. Once we know that, right, we know then how many moles of ammonia we started with, and we know what the original volume was as well. And so then from there, right, we can just simply divide the number of moles by the volume, right, and then we get what the concentration is in that scenario. So right, so let's do that right there. So we have the first things first, right, calculate the number of moles of HCl, and so that's just simply going to be the concentration. So that's 0.0105, right? And that's moles per liter times the volume, right? And so that's given in milliliters. So I'm going to convert that into liters real quick, right? So that's going to be 36.78 milliliters times. And so there's 1 liter for every 1,000 milliliters. Right? And so what we get here, right, milliliters cancel, liters cancels, we're only left with moles. So if we take our calculator and plug all that in, right, so we have 0.0105 times 36.78 divided by 1,000. And so what we get is 3.86 times 10 to the negative 4 moles, right? So that's how many moles of HCl we have. We know that the moles of HCl is going to be equal then to the moles of ammonia that we have present in our solution. So we know that, right? And so that's going to be equal to that right there as well. And so now to get the concentration of NH3, all we have to do is just simply take the moles of NH3, divide them by the volume of that solution. And so what we have is 3.86 times 10 to the negative 4 moles divided by 25 milliliters, right? So that's just simply 0.025 liters. And so what we get in this case is 3.86 times 10 to the negative 4 divided by 0.025 is a concentration of 0.01544 molarity, right? Which, let me just double check. B5, right? Which is what I have on the key. So That's all it is, right? In that case, right? So identifying like what the equivalence point actually means, right? So we know then what the initial concentration was of the ammonia, which is great. And so what we can then do is for part C, right? It asks what is the pH of the aqueous solution at the start of the titration before any acid is added, right? So this is just simply a weak base pH calculation, right? And so if we write out what the equation is in this case for this part, so that is, right, we have NH3 aqueous plus H2O liquid is in equilibrium to form NH4 plus aqueous plus OH minus aqueous, right? So that's our the reaction, right, that we're going to be looking at. So if we set up our ice table in this case, right, so our initial concentration was 0.154 molarity, right? We don't care about the water, right? And then we have 0 for the ammonium, and we have 0 for the OH minus. So now, right, we're going to lose X of NH3. We're going to gain X of NH4 plus. We're going to gain X of OH minus. And so then our end result should be 0.0154 minus X. And then it's going to be X. And then X right here. So if we write out our equation, right, we have Kb is equal to the concentration of ammonium, right, over times the concentration of OH minus over the concentration of NH3, right, just standard equilibrium expression. So we plug in our values that we have. So we have X times X over 0.154 minus X. And so those two X's up there, right, I can just simply write that out as X squared. So we have that. And so then the Kb value that we have is 1.76 times 10 to the negative fifth. 1.76 times 10 to the negative fifth. In this case right here, right? So we have that. So what we can do is we can just simply attempt the 5% calculation first to keep things simple for ourselves, right? So the 5% approximation is that basically we can consider the X right here to be negligible, right? That it's just going to be so small that it's not actually going to change really, you know, based off of sig figs, the concentration of the actual weak base that's part of it, right? The starting material, it's right, it's going to be so minimal in that case, and that makes it a lot easier to do the calculation, because what we can do now is we can then set this up so that we have X squared is equal to, right, now I'm just going to simply multiply 1.76 times 10 to the negative fifth times 0.15, I forgot 0. That's a very easy way to mess things up. 0.154. Right, so we have that, and so now that's going to be equal to 2.71 times 10 to the negative 7. And so we take the square root of that. What we get is 5.21 times 10 to the negative 4. Right? And so that's then going to be the concentration of OH minus in that scenario. So what we can do now is we can just simply calculate. The easiest way for me, right, to calculate pH from an OH thing is always if you just simply think about the fact that pH plus POH has to equal 14, right? So that's the relationship between those two. And so if they're, right, so if you have that, you can then rearrange that. So you have pH, right? So let me just write this out instead of talking about it, right? So we know that we have 14 is equal to pH plus POH. So that means then that pH is going to be equal to 14 minus POH in this scenario. And POH, right, is equal to the negative log of the concentration of OH minus. And so from there, right, we can just simply plug that in. So we have pH is equal to 14 plus the log of OH minus, right? Because negative times negative gives a positive in that case. And so we can just simply plug that in. So we have pH is equal to 14 plus the log of 5.21 times 10 to the negative 4. And so that should be equal to 14 plus the log of 5.21 10 to the negative 4. 10.7, right? And that is what, 10.72. Yeah. So, right, if I were to round up the next number and have it be 2 afterwards, right, that's what you would get. Right. And so that's how you approach that part of the problem, right? So initially, right, you're going to be in that region where you don't have a significant amount of the ammonium that's present, right? So you have to simply approach it from a weak base equilibrium perspective, right? And that's how you do that right here. And so one thing that I forgot to do, right, is that I didn't check whether the 5% rule counted. So the way that you do that is you just simply take your X value that you have, right? So the 5.21 times 10 to the negative 4, and you divide that by the initial concentration of the ammonium that you have. So that's 0.0154, right? And so I have this. And so what I got is 0.0338, right? And so if I multiply that by 100, that comes out to being 3.4%, right? So there was only 3.4% that was ionized of the initial amount. That's less than 5%. So this approximation is perfectly fine, right? You're not going to get too different of a value if you were to go through like the perfect route, right? And I think if you were to plug it into the your quadratic equation calculator, right, you wouldn't get anything that's dramatically different from what I have right here, right? And so that's how you would approach that right there. Part D, right? So what is the equilibrium concentration of H3O plus, OH minus, NH3, and NH4 plus at the equivalence point, right? So, excuse me. So what we know, right, is at the equivalence point, what happens is that you have NH3, right? That's reacting with H3O plus to form NH4 plus and water in that case, right? So that's the reaction that's happening. So all of this right here, right, because these two are equal, that's going to then equal the amount of NH4 plus that you're getting. And so then what we can use is the number of moles of NH3 that we initially started with, right? So the moles of NH3 that we started with, NH3 initial, right, is going to be equal to the number of moles of NH4 plus at the equivalence point. And so if we go back, right, so the number of moles that we had was 3.86 times 10 to the negative 4. 86 times 10 to the negative 4 moles, right? So we know then how many moles we have at the equivalence point of the ammonium, right? Because taking a step back, right, like looking at the equation right here, right, or sorry, the sketch of the plot of how the titration is going, right, we're going to be at this point right here. And so that's the point where the NH3 concentration are moles, right, and the H3Cl number of moles are going to be equal to each other, and so they're going to convert everything into NH4 plus, and so that's why you have that right there. And so now the next thing, right, is to figure out the volume, right? So in terms of the volume, we started off with 25 milliliters, and then we added 36.78 milliliters to that. Right, so if we take that, add those two up, we have 25 plus 36.78. That comes out to a total volume of this solution now being 61.78 milliliters in this scenario, right? So 61.78 is where we're at in terms of volume. So now if we calculate the concentration of the NH4 plus, right, all we have to do is take the number of moles that we have here. So we have 3.86 times 10 to the negative 4 moles divided by that volume. So that's 61.78 milliliters, right? And then we can convert that into we can convert that into liters, right? So that way the molarity is there. So we have then, multiply that by 1,000 milliliters over 1 liter, right? That way the milliliters cancel, so we have moles over liters. So we take this right here. What we get is 3.86 times 10 to the negative 4 divided by 61.78, right? Multiply that now by 1,000. And so what we get is that the concentration at the equilibrium point, right, is 0.06 in this scenario. Right, which is less than right what the initial concentration of the ammonium was, right, which makes sense because the volume is higher now, so it's been diluted down, and so that's going to change what's going on. But now we know what that is. So the next thing is, and so I'm just going to simply move on over, like, and so it's going to cover underneath, you know, part E, but part E is just simply basically part of part D. But what we can do in this scenario, right, is that we can then just simply figure out that you know, because the dominant species now is the ammonium ion, right, the NH4 plus, that means that we have to write out the weak acid dissociation reaction for that, right? So now the dominant reaction that we have in the solution is NH4 plus aqueous plus H2O liquid is in equilibrium to form NH3 aqueous plus H3O plus aqueous, right? So we have that right there. So we have our ice table now that we can set up, right? So we don't care about the waters, but NH4 plus, right? We have 0.00625 molarity, right? We can just simply, right, for simplicity's sake, consider and say that the concentration of NH3 and H3O plus is 0 initially, right? Because now we can calculate out what the equilibrium is, right? So these become 0 in this case. And so now we're going to lose X of the NH4 plus. We're going to gain X of NH3. We're going to gain X of H3O plus. And so then now the end concentration is going to be 0.00625 minus X. And this is then going to be X. And then this is going to be X right here. So now, the thing to do, right, is we just simply set up our equilibrium expression, right? So what we have is Ka now is going to be equal to the concentration of aqueous ammonia times the concentration of H3O plus over the concentration of NH4 plus. Right? So we plug in our values that we have from right here. So we have X times X over 0.00625 minus X, right? And so those two X's up top, I can just simply delete that, turn that into an X squared, right? And so that's now going to be equal to the Ka. So we have to also calculate out what the Ka is in this case, right? And so the Ka is just simply going to be the Kw over the Kb, right? And so that's going to be 1 times 10 to the negative 14 over, what was it, 1.76 times 10 to the negative 5th. And so that comes out to being 1 times 10 to the negative 14 divided by 1.76 times 10 to the negative 5th, 5.68. Oh, 5.68 times 10 to the negative 10. Right? So we have that right there. So now what we can do is make our lives easier, and we can try to attempt the 5% approximation again, right? Where we just simply consider that X to be negligible. And so what we get then is X squared. X squared is equal to, so I'm just going to multiply 5.68 times 10 to the negative 10 by 0.00625. And so what I get is 3.55 times 10 to the negative 12. And so what that gives us then is X is equal to, right, if I take the square root, is 1.88 times 10 to the negative 6. Right? So that's what X is equal to in this case right here. And so we can then do quickly the 5% check, right? So if we take 1.88 times 10 to the negative 6, divide that by 0.00625, multiply that by 100, what we get is 0.03%, right? So we're very much within the 5% approximation, that we don't have to, that the X is completely negligible in that case, which is great, right? Because that makes our lives a lot easier. So yeah, so we have that, right? So now we have X. And so now that we know X, right, we can figure out the concentrations of everything then at the equivalence point. And so at the equivalence point, right, you're going to have the concentration of H3O plus is going to be equal to 1.88 times 10 to the negative 6, right? Because that's equal to X. That's also going to be the concentration of the NH3 in this scenario, right? Because both of those are going to be equal to X. The concentration of NH4 plus, right, is going to be 0.00625 minus X. But if we do that real quick in our calculator, right, so we have 0.00625 minus 1.88 times 10 to the negative 6, right? What we get is 0.00624812, right? And so because we have 3 sig figs, right, we're going to round up that 8 to 5, and it's going to end up still equaling 0.00625, right? Which is why that 5% rule kind of holds, right? Because, you know, it's such a negligible, especially when considering sig figs amount, that doesn't actually matter, right? So we know then that the concentration of NH4 plus is still going to be 0.00625 molarity in that case, right? And so that's going to be molarity right there. Right, so we have all of those things. Last thing, right, is to calculate the concentration, of OH minus, right? And so concentration of OH minus in this case, again, we can just simply use the fact that we know what Kw is, right? And Kw is equal to the concentration of H3O plus times the concentration of OH minus. So we want to calculate the concentration of OH minus. We just simply take Kw divided by H3O plus in that case, right? And so this is just simply going to then be Kw divided by the concentration of H3O plus. So that's just then 1 times 10 to the negative 14 divided by 1.88 times 10 to the negative 6, right? And so what that gives us then is, and I'm going to run out of space, so I'm going to draw that somewhere else real quickly in a second. 1 times 10 to the negative 14 divided by 1.88 times 10 to the negative 6. So what we get is concentration of OH minus is equal to 5.32 times 10 to the negative 9, right? And I believe all of that matches, right? So I have 5.31 times 10 to the negative 9, right? Close enough, right? Probably a sig fig thing somewhere, right? 6.25 times 10 to the negative 3, right? That's, you know, the same thing as 0.00625 molarity for the concentration of ammonium. And then the concentration rate of H3O plus in H3, 1.89 times 10 to the negative 6, right? I have 1.88. So close enough, right? It's probably just simply a rounding difference somewhere. So that's how you do part D, right? And so now the last question is, right, what is the pH of the solution at the equivalence point? We know what the, and so I'm just going to simply, let me just block that off right here. I'll just do that math right up here, right? We know what the concentration of H3O plus is, right? So the pH is equal to the negative log of H3O plus. And so that, in this case, is going to be negative log of 1.88 times 10 to the negative 6. So plugging that in gives us negative log of 1.88 times 10 to the negative 6, 5.73, right? 5.72, close enough, right? Again, it's just probably a rounding difference somewhere between what I was doing it on the key and when I was working it through right here, right? So, but they're pretty close and everything. So yeah, so right, so that's how you work your way through B5, right? So again, the key thing for any of these titrations is really knowing where within the region you are, so that way you can, you know, properly apply the right approach, right? So, you know, when you're starting off any titration, you always have to then simply do either the weak acid or the weak base, you know, equilibrium approach that you would normally do in that case. When you're in the buffer region, which we didn't do in this problem right here, right, you can use the Henderson-Hasselbalch equation, right? You don't have to go through the whole messy thing of doing an ice table necessarily, right? When you're at the equivalence point, at that point, you then have to flip. So if you were starting off doing a weak base equilibrium like we did right here, right? At the equivalence point, then you switch to doing it as a weak acid, you know, equilibrium problem. And then if I were to add any more acid to this right here, at that point, all you have to do is you just simply have to subtract out the number of moles that were neutralized by the NH3, and everything else that remains, right, is just simply the moles of H3O plus, and then you just simply solve it that way, because any type of equilibrium that happens right here is going to be completely negligible, right? So if I were to add, you know, another like 5 milliliters of that HCl solution to this solution right here, right, if we're looking at the number of moles of H3O plus that we're at right now, right, 1.88 times 10 to the negative 6. If you're adding more HCl to it, right, that's going to be completely negligible, right? Everything is just going to be completely pointless, right? The H3O plus that you're getting from the HCl is going to completely overwhelm whatever NH3 you have right here, right? So that's not going to neutralize it anymore, right? Because it's going to be completely on a different scale and stuff, right? And so but again, right, those are the things to think about in those cases. So